We have y equals 1 minus cosine x over sine x. There's two ways that we can do this. You can use the quotient rule here, or you could rewrite that. We could rewrite that as 1 over sine x minus cosine x over sine x, and then take the derivative.
Why would you do cosine x over?
Wait, would it be like negative cosine x?
Would it be like
1 over sine x minus cosine x over sine x. You could do that. Cosecant x minus cotangent x. Yes, we could that this is equal to the cosecant x minus the cotangent x. I ran out of room there, but we want to take the derivative, and we'll take the derivative the first time using the quotient rule. So if we do that, the derivative, it's the denominator times the derivative of the numerator. What's the derivative of 1 minus cosine x? Sine x. Minus, because the derivative of the cosine is of a negative cosine is going to be a positive sine. Okay, 1 minus cosine x, and the derivative of the sine is over sine squared x. All right, so here we've got sine squared x minus the cosine of x plus cosine squared x over sine squared x.
how is that distributed?
Cosine minus cosine squared, and then I distributed the negative in the front. Correct. All right. Sine squared x plus cosine squared x equals 1. So we have 1 minus the cosine of x over sine squared x. And there's some different ways that we could look at that, but I'm just going to leave that there for right now. Okay, so this is one form of the derivative. There can be many correct forms of the derivative. So when you get a derivative and you look in the back of the book, just because your answer doesn't match the back of the book does not necessarily mean that you're wrong. There are just more than one way to do it. Sine squared plus cosine squared.
So you couldn't like cancel out sine squared x?
No.
Can't do that?
No.
Never?
Never. If you were multiplying sine squared times everything else, if it were a factor, you could, but not if it's a sum or a difference.
Isn't the derivative of sine x cosine x?
Yes.
Error.
How'd you get positive?
Here?
Yeah, it says positive cosine squared.
Because I multiplied here.
Cosine x now.
Cosine minus cosine squared, but minus a negative becomes a positive.
Oh.
Right here. Right there, that became a plus.
Okay.
All right, now let's look. What was the other form that we had? Y equals cosecant x minus cotangent x. We said that was another form of that same problem. What is the derivative, Justin, of the cosecant?
Negative cosecant x, cotangent x.
Good. And what's the derivative of the cotangent?
Negative cosecant squared x.
Negative cosecant squared x.
Nothing's kind of.
All right? This negative became a positive because that was a negative cosecant squared. Now what should I do next?
Factor out a cosecant.
I could factor out a cosecant or even maybe a negative cosecant. We could do that. Let's see. That gives me cotangent x minus cosecant x. Is that getting me any closer to the previous derivative that I had? It'll get me there. I think it'll get me there. What am I looking for in the denominator?
Sine squared x.
Sine squared x. So let's do this.
X.
Let's.
Cosine over sine, and cosecant is 1 over sine.
She's smart, man.
You're right. Okay, so if we do this as a negative 1 over the sine of x, and cotangent is cosine x over sine x minus 1 over the sine x. We end up with cosine x minus 1 over sine x. Y'all keep in mind what we're looking for there. And if we multiply through by negative 1 over sine x, we end up with 1 minus cosine x over sine squared. So it worked out to be the same answer whether we simplified or not. And we could even change this up a little bit. We could do 1 over the sine squared. We could go back to what we had previously. So there's several different ways that that answer could be written. We are not simplified if we have negative exponents. So you want to be sure that you get rid of any negative exponents and be sure that you can combine like terms. If you can combine like terms, do so. Right? We know that a first derivative is designated just with a prime. Y prime, f prime of x, dy dx. If you take a second derivative, that's going to be y double prime, f double prime. In the dy dx form, it's usually d2y over dx to the second power. That means second derivative. A third derivative is y triple prime. And then d3. Just showing you different ways that it could show up. If you see that, you know you're taking a third, that means it's a third derivative.
D over dx or is it dy over dx?
dy over dx. Sometimes it might be written. If you have the function right here, you could have d and then the function over dx. But real often you see it as dy dx. You
Okay,
could
so
have,
so you just put in you put in just d over dx and then the function right next to it. That's what you said. Okay.
if you don't have the y here, there's your y. That's your y. All right, after the third, then they just start using numbers. The fourth is y to the fourth. That would be fourth derivative. You could use f to the fourth. So just different ways that you could continue with higher order derivatives. Pardon? And then finally, you could have the nth, which would just be y to the n, f to the n, just any miscellaneous derivative. That has to do with speed increasing or decreasing, because I have a note in my notes. And this is something we'll talk about. Hopefully you've talked about it in physics, but speed is increasing if the first and second derivative, in other words, velocity and acceleration, have the same sign. Speed is increasing if velocity and acceleration have the same sign.
Yeah, we talked about this.
Have you talked about it in physics? Speed is decreasing if they have different signs.
Makes sense. How could you be losing velocity when you accelerate?
Well, if you're going like a rocket ship leaving the planet, you're gaining speed as you go up, and since velocity is down.
That you're asking a physics question.